Okay, so today's warm-up question says, where do the charges come from when you turn on a light? That's number one. And the second one says, will either bulb pictured light up? If so, which, and why or why not? So let's start with the first question. When you turn on a switch to close the loop for a circuit, where do the charges come from? Everywhere. Yeah, they're already present in the circuit. Again, don't go fall for the misconception that the battery makes them. That is a common misconception. The battery does not make those charges. Those charges are already present in the circuit because the circuit contains wires and bulbs and a battery and all these other things that are of course comprised of atoms, and atoms already have those charged particles in them. Okay, and so the charges are already present in the circuit is your answer to that. And the turning it on or closing that loop, that's how you get the charges to flow, because now your voltage source can push those through. The second question says, will either bulb pictured light up? If so, which? Again, this is similar to yesterday's warm-up question where we're looking at which ones would be part of the complete closed loop. And if you trace the wire from the battery and you follow it, you can trace the direction of the charges in your conventional current model. They'll go here. They can't flow into bulb A because there's no way for them to get back out. Okay, and again, those charges repel each other. They're not going to bunch up in there. They're not going to go in there at all because there's already charges in there and those aren't moving. Instead, they'll flow in through the base of the bulb into B through this filament and then back out the side. That's what we learned yesterday, is that you have to contact both the side and the bottom of the bulb. So bulb B would in fact light up because the charges would have to flow through it on their way from the positive terminal of the battery to the negative one, but bulb A would not. Okay, so bulb A would not light up. And again, that's kind of your why. So go ahead and make sure that you have answered these warm-up questions in that assignment, as well as yesterday's if you didn't already do that. And then as I said, we do have notes today. Yesterday we talked about the basics of circuits and some of the equations that we use with circuits. And today we're going to talk about one of our main types of circuits, the series circuit. Everything yesterday was a simple circuit. We had just like one light bulb. Today we're going to look at when you have more than one component and they're placed in series. And you do have a homework assignment, 1202.2 series circuit problem set, as well as a reminder to bring supplies for your electric house project because you are building on Monday. If you don't have supplies, you can't really do much of anything, and that would be a bad thing because you need to be working on it in class. And if you lose one of those work days, I don't know if you'll be able to get caught up. Okay, so again, yesterday we talked about the two different types of circuits, series circuits and parallel circuits, but that's all we really did was mention that they exist and that we can arrange these components in different ways. Today we're going to focus specifically on series circuits, which is the one that you see here on the top of my screen. Here is an example of a series circuit. Okay, a series circuit is an electrical circuit where all components are connected end to end in a single unbroken loop, providing only one path for current to flow. Think of it like a television series. You watch one episode after the other, or a book series. You read one after the other. They're all on the same loop. And so if you were to follow these charges in this conventional current model, they're going to go through R1. And then R2, there are two resistors in series on the same loop. Okay, so this is an example of a series circuit. All of the charges have to pass through both of the resistors because there's not any other pathway for them. Okay, you'll notice when they do that you have energy change. We talked about that conservation of energy yesterday and the fact that however much energy gets put in at the battery will get dissipated at the resistors, but this time there's two. So if they're identical to each other, which this diagram is showing that, then you're going to have half of that energy dissipated at R1 and then the other half of it at R2. And we'll revisit that as well today when we talk about it again. So again, a series circuit is a circuit in which current has only one pathway to follow. There's only one loop. Again, the same rules that we talked about yesterday still apply for circuits in general. Your circuit must still have a closed loop and a voltage source. You have to have a battery and you have to have a complete conducting path without any breaks in it. And then the components in a series circuit specifically are added end to end on the loop. And so here's two examples. The one on the left shows 2 light bulbs in series. The one on the right shows 3 light bulbs in series, but both of them are series circuits. You could, of course, keep adding more if you wanted to and still have a series circuit so long as they're all on the same loop. Because the components are on the same loop, as you add additional resistors or light bulbs, it increases the total resistance of your circuit. That total resistance has a name. It's called equivalent resistance and a formula that you might want to copy down. But it's a pretty basic formula. As you add more resistors, because the charges all have to go through every single resistor, you simply add their resistances together. So when I say equation, that one's really basic, and it's on the formula chart. It says that the equivalent resistance in series is R1 plus R2 plus R3 plus ... however many you have. Okay, same thing here to Rn, however many you have. If you only have 2, it's just R1 plus R2, by the way. There wouldn't be an R3. But you just add them up, and that gives you your total equivalent resistance. So here's a example practice problem. You can sketch this one out if you want to. Find the equivalent resistance of this series circuit. If I have 3 bulbs, and each of them is identical, 2 ohms would be the resistance at each one, then my equivalent resistance is just my total, 2 plus 2 plus 2, which of course is 6. And so the reason it's called equivalent resistance is because this circuit would be equivalent to that circuit. If I had a single 6 ohm light bulb, it would be equivalent to having 3 2 ohm light bulbs in series. Okay, those 2 circuits have the exact same amount of voltage and the exact same amount of total resistance. And so if I wanted to find the current, it would be the same for both of those. Okay, if I want to find the current, we're going to use the equation from yesterday. V equals I times R. And we're going to plug in our voltage, which is 9 volts. We're going to plug in our total resistance, which is 6 ohms. Again, I can use my redrawn circuit that shows that equivalent resistance. And we're going to solve for I, which will be 9 divided by 6, which is 1.5 amps. And so the current in both of these 2 circuits, since they're equivalent to each other, is 1.5 amps. Okay, regardless of whether it's 3 light bulbs that are each 2 ohms or 1 light bulb that is 6 ohms, it's the same current for both, 1.5 amps. Okay, so again, you can still apply the stuff from yesterday, and you can apply this new concept of adding multiple resistances together to get your equivalent resistance. Here's what that would look like with the analogy that we were using yesterday. So here, this would be a single 6 ohm resistor, and you can see that this resistor has the same amount of change in voltage as these 3 do together. Each of these is a little smaller resistor. These are 2, 2, and 2. And so these two circuits have equal equivalent resistance, and they thus have equal currents. They have the exact same motion of those charges through them. And again, you can see both of them have that same downhill flow. It's just this one goes through 3 smaller resistors versus 1 larger one. Okay, equal amounts of current. Which is what I was mentioning. By the way, no matter where you measure the current in a series circuit, it will be the same everywhere. Okay, so if I measured my current at any of those red dots that are on my circuits up here, they would have the exact same current, whether I measured it before or after the bulb, or whether I measured it here in between 2 bulbs. It doesn't matter. The current, let me go back to this real quick. The current is the rate at which the charges flow, and you'll notice it's the same. The whole way through, they're moving at the same rate. Okay, and so the current will be the same everywhere in a series circuit because all of the charges are on the same loop. Okay, so they all have to travel the same speed. Again, you can write that down or copy this down. By the way, if you're trying to follow along, this is slide 38, if you want to open it up on your own screen. All right, here's 2 different circuits. One of them still has 3 bulbs, one of them still only has 1 bulb, and it says which series circuit has the greatest current. If you wanted to figure out what your current will be, you need to figure out what your resistance will be. You can calculate it with Ohm's law if you want to, but we don't actually have to calculate it. We know that current is inversely proportional to resistance. So if we figure out which one has more resistance, that one will have less current and vice versa. And so if I look at these, the B I already know. I already know the total resistance of B is 8. But A, I add those up. 1 plus 2 plus 1 is 4 ohms. And so circuit A has half the resistance and thus would have twice the current. Again, resistance and current are inversely proportional. If you wanted to solve it, you could. Okay, but this, because it has half the total resistance, even though it has 3 bulbs, those bulbs individually have less resistance. You do have to make sure to do the math. Okay, that because it has less resistance, it will have more current. And again, you can copy that example down if you like. All right, so again, what changes can increase resistance? We talked about these factors yesterday. If I wanted to increase the resistance in this circuit, I could use thinner wires. Okay, either throughout the whole thing or at those resistors specifically. I could use longer wires. I could use a less conductive material. So instead of using maybe copper, I could change that so that I was using titanium or something. Okay, but a less conductive material. Higher temperatures. Okay, and then if I added more resistors, obviously the more resistors I add, the greater my resistance will be. Okay, and so those are different factors that we've already talked about, but now we're applying them specifically to a series circuit, and it's the same ones that we talked about yesterday. Okay, so let's practice using Ohm's law in a series circuit. We already did it kind of a little bit, talked about it at least proportionally, but let's see if we can do some calculations for this circuit. And if you want to copy this down on your paper so you can refer back to it, it might be a good idea. This circuit has 3 resistors in series that are 4 ohms, 10 ohms, and 2 ohms, and it is connected to a 12-volt battery. I'm going to use a table like this, and I'm going to recommend that you do as well. In fact, one of the things you have to do in your RA is to put your answers from your calculations into a table like this, so you may as well get used to using them. And so we're going to fill in the table what we know. The resistances are labeled in the picture. 4 ohms, 10 ohms, 2 ohms, and I color-coded them to match how I labeled my resistors. I can find my total resistance really easily. I just need to add them up because they're in series. So 10 plus 4 plus 2 is 16 ohms. You just add them. Okay, and then we can fill in that 16 ohms into our table as well. Now, other pieces of information I can see in the circuit, I see the battery's voltage. That's the only other thing I see. The current isn't labeled for me. And so I'm going to go ahead and fill in my voltage of my battery, which will be 12 volts. And then from here, we know that the rest of these values in this table have to be calculated. Okay, and so I can start by calculating my current because I know Ohm's law, V equals I times R, and I have V and I have R for the total circuit. I can find I for the total circuit. Because the current, is the same everywhere in series, when I solve for my current, I'm always going to be using my total resistance. And the current will be the same everywhere. So once I find it for the total, it's the same at every other resistor in a series circuit. Okay, because there's only one pathway. Everything's the same rate, flow rate. Okay, so plugging in looks like this. 12 equals I times 16. Divide both sides by 16. And 12 divided by 16 is 0.75 amps. Okay, so that's the number you're going to fill in to the entire column, because your current is the same everywhere. That circuit with those 3 resistors is equivalent to a circuit with a single 16 ohm resistor. And so it'll have the same current everywhere, just like we talked about on the previous slides. Now that we know the current everywhere is 0.75 amps and we know the individual resistors, we can figure out what your change in electric potential will be at each of the resistors, your voltage drops. I do know that they have to add up to the battery. Remember, we talked about conservation of energy. The energy put in by the battery, which is the battery's voltage, 12 volts, will equal the energy that leaves. So I know that those 3 together have to add up to 12. Okay, and I can solve for each of them using Ohm's law. V equals I times R. Starting with resistor 1, it looks like this, 0.75 times 4, that's 3 volts. With resistor 2, it looks like this, 0.75 times 10, that's 7.5 volts. And with resistor 3, it looks like this. And guess what? Those add up to 12. Okay, fill them into your table. They add up to 12. Okay, and now that you have those filled in, there's only one column left, and that's power. And this is why the table's written like this. Because V is I times R, if you have the first 2, you can just multiply them and get V. And the power equation, was I times V or V times I. So now we just multiply these two to get power. So it's written in that order for a reason, because you can just multiply the two columns to get the third one and then the next two to get the fourth one. Okay, so again, here's similar to what this circuit is. Now this circuit wouldn't look identical to this. It does have 3 resistors, but those resistors aren't the same size. But I couldn't find a diagram of that. So, but this is basically what we're looking at. Again, those total voltages add up to the battery. Okay, even though they're not all the same as each other, they still have to add up to the battery. All right, power. Power is voltage times current. So for resistor 1, my voltage is 3 and my current is 0.75, giving me a power of 2.3 watts. For resistor 2, it's 5.6 watts, and for resistor 3, it is 1.1 watts. And so you can fill all of those values into your table. And you can get your total power either by doing the same equation, V times I for the total, or by adding together the powers. Either way. Okay, so either way, you're going to get the same thing, and that's going to be 9 watts. Whether you add together those individual powers or whether you do 12 times 0.75, you're going to get 9 watts. That'll be the total power dissipated by your circuit. That's how you apply Ohm's law to a series circuit. Okay, it's not too bad once you get the hang of it. And the table does help to organize the information, which is why we use them so frequently, and it's why you're going to have to do one in your RA as well. All right, follow-up question. If each resistor is a light bulb, which is brightest? You want to add this to your notes. Power determines brightness. If you can calculate the power, you will know which one is brightest. And we just calculated the power. Okay, let me go back real quick. The power was greatest at resistor 2, 5.6 watts. That's going to be your brightest bulb because it has the most power. Okay, but the other thing you can do is in series, since power is voltage times current, and in series current's the same everywhere, you can just relate it directly to the voltage drop. Okay, if you hadn't calculated power yet. And you're going to have the biggest change in energy when you have the most resistance. So if you look at a series circuit and you find the one with the most resistance, 10 ohms, that one will be brightest. That rule only works for series, which is why you can always go back to power, but if you apply that concept to a series circuit, the one with the most power dissipated will be the one with the most resistance. Okay, so again, if you want to make a note of that, by all means, please do so. Any questions about those calculations or this concept of bulb brightness, if these are light bulbs? All right. So yesterday we talked about Kirchhoff's laws without actually calling them Kirchhoff's laws. We talked about conservation of charge and conservation of energy. And those are going to form these laws. These laws form the foundation for circuit analysis and describe current in a node and voltage around a loop. So just to make sure you know what we're talking about and we have the same vocabulary, a node is any point, junction, or segment of wire where circuit components connect. So where two things connect to each other, that's a node. A loop is any closed continuous path that starts and ends at the same node, so connection point to the battery typically, passing through components like resistors, batteries, whatever on the path. Okay, and so when we use these terms, I want you to know what they mean. So let's go ahead and take a look at Kirchhoff's first law, which is also sometimes called the junction rule or the current law, and it's based on conservation of charge. We talked yesterday about how conservation applies to circuits, and the first law is basically conservation of charge. It states that the sum of all currents flowing into a node equals the sum of all currents flowing out of the node. This means that the current flow out of a battery equals the current flow back to the battery. So you have the same number of charges that leave as you have that come back in because you don't lose any along the way. Conservation of charge. That is the first law. And you can apply it to a series circuit or a circuit that has only one resistor, or when we talk about the other ones later on, you can apply it to parallel circuits and combination circuits, which we will do when we discuss those. Okay, so if I were to look at this as it applies to this series circuit, again, my current flow is the same everywhere, which we already said. That's basically what Kirchhoff's first law says when it applies to a series circuit. Then my current flow out of the battery equals the current flow back in. The current flow into any node equals the current flow out. Okay, and so it has to be the same everywhere because everything's on the same loop. So if you measured your current at these 3 different places with ammeters A1, A2, and A3, it would be the same. Your current is equal everywhere in a series circuit because there's only one loop. That is the application of the first law to series circuits. Second law. Second law is called the loop rule or the voltage rule, and it's based on conservation of energy. Okay, it states that the voltage drops at the resistors or bulbs along a loop must add up to equal the voltage of the battery. It states that the sum of your voltages around a loop is equal to 0, and that's because the battery is positive and the drops are negative. If you think about the picture we saw, the battery lifts it up and then it falls back down at the resistors. Again, it's an analogy, but it just means your total energy change is 0, conservation of energy. Okay, but it's based on conservation of energy. It's also sometimes called the voltage rule or voltage law. So again, if we look at the voltage drops here, they have to add up to the battery. In this case, they would have to add up to 24 volts. And so if you calculated each one, you could figure out what those voltage drops are. Now, if all of these were the same, let's say that these were all the exact same resistance, 2 ohms, whatever, for each of them, then I wouldn't have to really do math here. I would just say my voltage drops are all equal because my resistances are equal, 24 divided by 3. And I could do that. Okay, but because they're not equal, you'd have to go back to Ohm's law and calculate each separately, but it will be proportional to their resistances. Again, you can see it here. These two are equal to each other, and so the voltage drop in R1 is equal to the voltage drop in R2, but they have to add up to the battery. That's the whole idea, okay? However many you have, they add up to the battery's voltage. Here's 3 of them, same thing. They add up to the battery. So the battery adds energy in, and then it gets dissipated at those resistors. And so along the loop, your total voltage adds up to 0 because the battery's, let's say, plus 12, and those 3 together are minus 12, or whatever. All right, that is it for today's notes. So for the rest of the period today, you now have time that you can use to work on your problem set 1202.2. You've got about 28 minutes. So you've got a fair amount of time to probably finish this thing. But obviously, if you don't finish it in the room today, you can work on it for homework. The other thing that you need to do, if you haven't already done this, you should have already turned in your planning sheet for your house project, but you do need to make sure to have a quick conversation with your group, maybe even set up a group chat or something. Obviously, you can't take your phones out right now, so you would need to either write down numbers or snaps or whatever you want to do on paper, or make some kind of Google Doc and put it in there. I don't care. But figure that out so that you can help each other remember to bring your materials on Monday. Okay, because you guys need to bring in everything except for the light bulbs. We will provide those, but anything else you have to bring. That means you're bringing in your own cardboard or shoe boxes or aluminum foil, tape, all that stuff. So make sure that you know who's bringing what and make sure that you bring it into class on Monday. If you have questions, please let me know. Otherwise, I'm going to let you guys get to it. You're working on 1202.2, series circuit problem set.